Like many developers, I love working on code performance, getting deep into a problem, measuring, profiling, tweaking, squeezing out every last drop of juice from my code. As a Rails backend developer, I don't get to do this very often, but last year I had this project where performance was key. And working on that project, I learned some interesting lessons. This is a talk about assumptions. First of all though, hi, my name is Daniel, and I work for a company called GoCarless. We are a payments company based in London. As you probably noticed, I'm not originally from London, I come from Argentina. So in case you were wondering, that's the accent. Now, before I get into the interesting bit of this talk, I need to give you a little bit of context about the problem that we were trying to solve. GoCarless is a bank-to-bank payments company. We are basically a sort of API on top of the banking system. Now, when you're a payments company, your customers expect you to always be available, just like they expect their electricity to always work. So for us, uptime, this line works better in Europe, I guess. So for us, uptime is critical. And among other things, that means having good metrics for your apps is critical. Now, one of the main tools we use is a metrics server called Prometheus. Now, we love Prometheus, but we had a pretty big obstacle trying to get it working with Ruby. The way Prometheus works is it basically keeps a history of all of your metrics and how they looked over time. And to get those numbers, Prometheus will periodically hit your app asking for them. So in order to have metrics, you're going to have your web server that's running your app. And in addition to that, it has a bunch of counters in it, say how many HTTP requests you served, how long they took, how many payments you took in different currencies. Prometheus will hit your app every few seconds asking for those numbers, and your app returns something that looks a bit like this. Now, Prometheus also has libraries that help you do this. These libraries run inside your app, and you use them to declare what your metrics are going to be, set their values, and then when you get scraped, they automatically generate this output. And there's one of these libraries for all major languages. There's one for Go, there's one for Java, and of course, there's one for Ruby. Now, for most languages, the story ends there. But in Rubyland, and by the way, also in Pythonland, the story is a little bit trickier because Ruby and Python have a global interpreter lock, or GIL, which doesn't let your code run in multiple threads at the same time. Because of this, our web servers are usually not multi-threaded. That doesn't scale very well. Instead, in Ruby, we tend to have separate processes. Processes don't share memory, which ends up solving the same problem the GIL is trying to solve, and everybody can run in parallel, happily ignoring each other. Now, the way this works is when Unicorn starts, it will load your app, and then it forks itself into a master orchestrator process and a bunch of worker processes that are actually working on your requests. When a request comes in, Unicorn will pick some worker that is free, send it your request, and takes the response and sends it back to the client. This system works great. It scales really well across cores, and is how most Ruby applications are running in production. But for the Prometheus use case, this is a problem because now that we have separate processes and they don't share memory, which was the whole point of having them, each process has their own counters. When Prometheus polls you and asks you for the numbers, the master process will pick one worker, and that worker will report its numbers. But this is never what you want, because this is only a partial view of the system. What you want is that global view of all of your processes added together. Now, because these processes don't share memory, there's no way for any worker to actually see the numbers in the other processes to add them together, right? Which is by design, and it is the main reason we use separate processes, but for Prometheus, this doesn't work. And since the Prometheus library, basically the Ruby one, doesn't support this cross-process aggregation, that means most Ruby projects that want to use Prometheus basically can't. And we were definitely on this boat. We wanted to have Prometheus for our main Ruby app, and we couldn't. And it wasn't just us. This has been the case for quite some people for a pretty long time. So we decided internally we would rewrite the library to solve this particular problem, plus a few other small issues that it had. But there was one more thing to consider. The Prometheus maintainers really care about performance for these libraries because instrumentation should be free for your app. If you want to increment a counter inside a tight loop, for example, you should be able to do that and not even notice it. And buried in that long discussion for 2015, we had a target. Now, one of the main maintainers basically said that incrementing a counter shouldn't take more than a microsecond. Now, another of the main maintainers who had more experience with Ruby was like, you're not going to be able to do that. To which the first guy reasonably responds, I mean, surely Ruby can't be that slow. Which leads to one of my favorite responses ever. I guess there's a reason people like writing C extensions, right? Now, I don't know about you, but if you had asked me back then whether you could do this thing in a microsecond, I would have had no clue, because I have no intuition of Ruby performance at this level. Now, to store our numbers, we use hashes instead of just plain integers for reasons that are going to make a bit more sense later. But for now, what I mean by that is, when I say increment a counter, what it means in practice is reading and writing a value in a hash. And according to this exchange, this either could or couldn't be done in a microsecond. And the problem I have with that is, this is such a tiny scale that, compared to my usual experience, I have no idea how long that may or may not take. What I mean is the following. Imagine that this here is a second. Now, those are 1,000 squares, 1 millisecond each. As a web programmer, this is how I see the world. Time exists in boxes of milliseconds. There's nothing smaller than that. So I'm running my web app, and a request comes in. There's a couple milliseconds that are taken by Unicorn, Rack, middleware, Rails, I don't know. Before it even hits my code, I lost like 2 milliseconds. Now this request has a user ID in session, so we're going to hit our database and to load that user. It's a well-indexed table, so let's say it takes a millisecond. This page we're loading is a list of orders for this customer. So we hit the database to load the orders, and we hit it again to load the line items for those orders. Then we hit it a bunch more times because we had an n+1 that we didn't know about. Oops. We check a couple of feature flags in Redis, which is really fast, but it's still at the other end of a network cable, so it takes about a millisecond. And then we take all of this information and we render the view, which is actually quite big, so it takes a while. So that was what, 60, 70 milliseconds? That's reasonable for a Rails app. This is on a good day. On a bad day, may look a bit more like that, right? Now, this is basically my daily life as a Ruby developer. This is where my intuition works. This is where, if I need to care about performance, I know roughly how long things should take, and I know where to look if something looks odd. But for other developers, this is very different. For example, if you're a game developer, you live and die in 16 millisecond buckets. If your game is going to run at 60 frames per second, you have 16 milliseconds per frame, non-negotiable. In those 16 milliseconds, you need to process your inputs, run your AI, your physics, your collision detection, all of your game logic, then take all of that info and render a beautiful frame. And if you miss the 16 millisecond boat, you skip a frame, your game stutters a little bit, and thousands of angry gamers shout at you on Twitter. It's a little terrifying as a Ruby dev how strict that is, right? And if you're a high-frequency trader, you're just dying of laughter right now. Like 16 milliseconds, it's an unthinkable luxury. If you take one entire millisecond, you're dead in the water. You can't even play this game. So the point I'm trying to make here is that what's fast and what's slow is really, really very relative. I mean, you have some people over here that are trying to get their memory to be all together so that the CPU caches are always full and they shave some nanoseconds. Whereas I'm in milliseconds land trying to not hit the database too often, right? Like, it's such a difference in scale that it's insane. And this is something that's very important to keep in mind when you're talking about performance or when you're reading about performance. Some things that, to me as a Ruby dev, are amazingly fast, somebody that's writing drivers inside the kernel can't even consider them because of how slow they are for them. So keep that in mind when somebody says that something is fast or something is slow. This is literally meaningless without a context. But we don't think about this most of the time. We just go with this is fast and that is slow, and we internalize it as if it meant something. Now going back to our original questions, can we do this thing in a microsecond? Well, as I said, I'm used to these sorts of time. It's like, for most part of my work life, time exists in boxes of a millisecond. I cannot care about anything smaller than that. I have bigger fish to fry. So if you say, can I increment a hash, this tiny, tiny thing, in a microsecond does this much. In case you can see that, it's that tiny dot over there, right? So if you ask me this, like, I have no idea. I live in milliseconds land. But we have two opposite opinions here. Surely we can figure out who was right, right? Well, the fun thing is, they both kind of were. Now, let's go measure and see what we find. The first problem we're going to find is even measuring this isn't straightforward, because when the thing that you're measuring is this tiny, the code that's measuring is actually a significant part of your runtime. Now, if you manage to work around that, you're going to find that you can do this about 12 times in a microsecond, which is amazing. This is well within our budget. And it looks like that's it, right? Like, we have our answer. First guy was correct. Ruby isn't that slow. You can totally increment the hash in less than a microsecond. Except, it's not really that simple in our case. Now, I said before, we're using hashes instead of integers to store our counters. But why? Why are we using hashes? Well, the reason is you normally want more resolution than for your metrics than just having one number. For example, of payments, you don't just care about how many payments you took, you care about, for example, how many you took in each currency. So we have this concept of labels. Basically, each counter is tagged with these key value pairs called labels. And we store these counters in hashes whose key is also a hash that has those labels. And that means that incrementing those numbers over there is actually going to be much slower than we were using constants for the keys, like in our measurement before. Because now, when you're finding your value inside the hash, you need to be comparing hashes to hashes instead of constant to constants, which is much slower. Now, how much slower depends on how many labels you have. If you have 3 labels, for example, that is terribly slow. But if we consider the best case scenario, which should be the majority of cases where you don't have labels, it's a bit better, but it's still 9 times slower. And you can see that we're already kind of getting close to our limit. And we're just incrementing a hash here. In real life, we need to do some validation and some processing all these labels, and we're not even thread safe. You put a mutex around this to make it thread safe, and now you're at a microsecond and a half and you blew your budget. So it turns out, guy number 2 was right in the end. We can't do this in a microsecond. But what I think is more interesting is not which one of these 2 was right. What I wanted was an easy answer, right? I wanted one of these guys to win. But reality is more nuanced than that. And this is what I'm talking about when I say that fast and slow are meaningless without a context. It's always more nuanced than that. Bottom line, we're not going to be able to hit our target. We already passed it and we're still in a single process. But we shouldn't throw the baby out with the bathwater here, right? Like the important thing is, because instrumentation shouldn't affect your performance, we want this to be as fast as possible. And because this is going to impact lots of projects for lots of companies, we want to, it's worth investing a lot of time into actually making this as fast as we can. So with that in mind, how do we share these numbers between processes with basically as fast as possible? Well, we experiment a lot. Basically, what we started doing at this point is try everything we could think of. And I'd like to walk you through four of these experiments that we did. First up, let's make this real easy for ourselves. Ruby has this unusual data structure called a p-store. Basically, it's a hash backed by a file on disk. Every time you set a value, the whole thing gets serialized and put into a file. Every time you read a value, the whole thing gets read from disk and you get your value. And the file has a lock around it. So you can actually read and write the same file for multiple processes all at the same time. Everybody sees the latest data and it will be safe. And if you think about it, this is exactly what we need, right? I mean, we have this global hash that's shared by everyone. All the processes see all the data, and we're done, which is great. But is it going to be fast? And as you can probably expect, it's not. It's not going to work at all. Now, if we take a little step back, what are we trying to do here? Well, basically, we're trying to have a chunk of memory that is shared between all of the different processes. And as a complete side note, one of the great things about working in my company is the amazing people I get to work with. Now, granted, some of those people are trolls, but the trolls sometimes have good ideas. I mean, SQLite was probably not going to be the best way to do this, but he got me thinking, you know what's a great way of having a chunk of memory shared between processes? Is my good old friend Redis. Redis is basically that. It's basically a chunk of memory running in a separate process to your app. All of your processes can read and write it, and we all know it's super fast, right? So this is exactly what we need. And actually, the Prometheus library for PHP uses Redis for the same reason, so this was very promising. So I wrote the code to use Redis as a backend. I was super excited because I knew this was going to be the solution. Fired on my benchmarks, and it turns out it was really disappointing. I mean, it's slower than just dumping the entire hash to disk every time. Now, I was pretty sad when this happened because I thought I had it. But more importantly, how? How can it be this slow? I mean, isn't Redis supposed to be super fast? But if you stop to think about it, it kind of makes sense. Now, you talk to Redis over the network. Even if it's localhost, every time you touch it, you need to make a packet, put it into a socket, send it over the network, Redis gets that, opens it, parses your command, runs it, makes another packet, sends it back to you. There's a lot going on. Redis is super fast for a database. Like, it normally lives in its own server. You talk to it over the network, and those 60 microseconds we just saw there, they're nothing compared to the network round trip. So it's really fast compared to other databases out in the network, but compared to something that happens in your own machine, in your own process, like writing a tiny file, never even had a chance. So as I keep saying, fast and slow without context are meaningless. Now, at this point, I had no choice but to face the giant elephant in the room. The consensus from pretty much everyone on how to solve the multiprocess issue was that we should use memory maps for this. This is what the Python library does, for example. But during most of the project, I was trying really hard to avoid them. I really wanted to find another way because I didn't know them very well and they felt a little bit dangerous, and you'll see what I mean in a minute. Now, what a memory map lets you do is have a shared memory map file. The way this works is a process opens a file and maps it to a page in memory. If you read that memory, you get the contents of the file. If you write to that memory, the file eventually gets updated whenever the kernel feels like it. But here comes the magic. If a second process opens the same, maps the same file, they both get assigned to the same page in memory. So now when one of them writes to that page, the file will get updated later, but you don't care about that. What you care about is that when any of the two processes can read that page and get the latest data, which is magic. And the other thing you also care about is that there's a file, but you're not writing directly to the file. You just write to memory, which is as fast as writing to memory, not as slow as writing to a file. So again, this sounded like the perfect solution. There's only one problem. mmap is a syscall. Do you guys know how you do a syscall in Ruby? You don't. You do it in C. Now, granted, there's this thing, which has the most hilarious line I've ever seen in official documentation. But it's not particularly useful for this. And let's say you actually manage to call mmap with this thing. Now you have a chunk of raw memory that is yours and a pointer to it. Now what? What are you going to do with that, right? So what we need here is some sort of extension, some gem written in C. And I don't write C. I can barely read it. And I should definitely not be trusted to write C code that deals with a syscall that I don't know very well, and does some magic memory voodoo, which is going to run not only in my company, but in a bunch of other companies. This is not going to happen. But fortunately, there is a gem. It's maintained by Tenderlove these days. And to use it, basically, you create a file, you initialize it to a certain size, say 1 megabyte, and then you init this mmap class. And now you have this m variable, which behaves sort of like a byte array, thanks to a bunch of magic that this gem is doing. And so if you have a bunch of bytes to write, you just set a range in this array, and that'll do it. Now, the tricky bit is turning the stuff you want to store into a bunch of bytes. To do this, you use these methods called pack and unpack, which basically convert your Ruby stuff into bytes and then back into Ruby stuff. But if you've never heard of pack and unpack, don't look them up. It's just, keep your innocence. It's one of the beauties of Ruby is not having to deal with this kind of thing, right? But we have a float in our case. Our counters are floats. Sorry, I lied before, they're not integers. But we have a float, and we wanted to write into this m thing, so we pack it into bytes, which takes 8 bytes, and then we set those positions on the array, and we're done, right? Like, couldn't be simpler. Now, how fast is this? Well, if you remember, these were our options so far. Memory maps, which as I mentioned, I really don't want to use, are actually quite fast, which is a bummer, because now I'm going to have to use them. And again, we're done here, right? Like, we have our solution. This shares the numbers. It's very fast. And I thought we were done too. But as soon as I started to use this more heavily, I got one of these. Now, raise your hand if you ever gotten one of these that was your fault. I have 3 hands, right? Exactly. You're not supposed to see this. This is a seg fault, which is precisely what I was afraid of. And here's the thing. One of my favorite things about high-level languages is not having to deal with this. Like, I don't want to have to deal with this. I don't know how to deal with this. I don't know where to start. Like, this is precisely why I don't do C. And also, this is a very obscure gem. I mean, not many people need to do memory maps. So there's nothing in Stack Overflow. I haven't found anyone actually using this. So it's kind of hard to figure out what I'm doing wrong. But this is what I managed to find out through a lot of trial and error. The problem seemed to be happening when that initial size I gave the file, that 1 megabyte, wasn't enough. So I have some code there that's going to resize it. And the seg fault only happens if that code runs, which is perfect. I have no idea why it happens, but at least I can reproduce it reliably, right? And so to solve this, we do what we always do with these kinds of problems. You just try random stuff until something sticks. which took a while because I had no idea what I was doing, but I ended up making the seg full stop. It was this elaborate dance of like unmapping, flashing the file, closing the file, reopening the file, resizing it, closing it again, then reopening it again, and then mapping it again, and somehow the seg fulls didn't happen anymore. Now, if you have a problem, you don't understand the problem. You try random things until the problem doesn't happen anymore, but you don't know why it was happening or why it stopped. How confident are you that that's not going to happen again in production, in some random server, in some mission-critical app, right? I really wasn't. I did not like this at all. So we kept looking a bit more. And this takes us to the last experiment, which was the biggest surprise in this whole project. Now, with the mmap, we're basically working with a file, and we're doing the kind of things you do with a file. We just happen to be doing it in memory, which is faster than using a file, right? But what happens if we ditch the mmaps and we just do this to a file? I mean, pretty much the only difference is that we need to call disk functions to jump around and to write. And that's pretty much it. And the interesting bit here is you're only writing the minimum amount possible. You're not Marshall dumping an entire hash. You're just doing one seek and writing 8 bytes. It's quite efficient. And that was pretty much the whole change. I mean, now we have no memory maps, no C, no segfuls, nothing fancy. It's just plain old boring Ruby writing bytes to old boring files, right? But as usual with these solutions, like we're hitting the hard drive now, we're writing files. How slow is this going to be? And before I tell you that, I want you to visualize how slow disks are. I mean, we use Redis and Memcached famously because they're in RAM and not on disk, right? We use RAM drives and TempFS, so we can have things that behave like disk but are not that slow. We give our databases just gargantuan amounts of RAM so they can keep everything there and not have to touch the disks because the disks are so slow. So how slow was this solution based on files? Well, if you remember, the mmaps were about 6 microseconds. Files on actual hard drives were about 9, which completely blew my mind. I mean, this is mad. If you compare this to memory maps, we have no external dependencies, we have no risky C code, definitely no segfaults. It's compatible with all editions of Ruby. It's code that every Ruby programmer can understand. And most importantly, there was nothing in there that kept me up at night. All of this for just 3 extra microseconds, this is a complete no-brainer. And that's it, we're done. I mean, we ended up going with disk as the end solution because it was fast enough. And we think that the trade-off is more than worth it for the peace of mind that this brings us. And this is where the talk should end. I mean, we solved the problem with a fast, elegant solution. We got our code merged. We're now maintainers of the gem, actually, which is quite nice. And now people can use Prometheus in Ruby, right? Happy times. But this is a funny result, isn't it? I mean, memory is supposed to be orders of magnitude faster than this, thousands of times faster. And I'm telling you as well, 30% faster? Like, what's going on here? And as I've been saying, it's always more nuanced than that. Now, there's a number of things happening, but mainly, if you're at all used to performance numbers with hard drives, you're probably looking at that number with a lot of suspicion right now. And you'll be right, because what's happening here is that I'm basically cheating. I mean, it's a fair cheat. It works for my use case, but I'm still cheating. You see, actually putting stuff on disk is really slow, but that's not what happens when your app writes to disk. When you tell the OS that you want to write to disk, the operating system takes note of that and goes like, yeah, all right, I'll get to that at some point. But it doesn't actually write to disk. It'll do it later, at its leisure, whenever it happens to be convenient. And normally this is a problem. If you are a database and somebody sends you data, would you trust this dude to actually write to disk? I mean, of course not, because when somebody trips on your power cable, you lost that data. Now, what you have to do is fsync, which is basically saying, hey, those things I tell you to do them now, I'll wait. And that is slow, because now you're actually writing to the disk. If you're a database, unfortunately, you really, really care about your data, so you're going to have to pay that price. But I'm just storing metrics for this particular run of my application, and if my app gets killed, nah. I mean, Prometheus has the numbers so far. Next run of my app, I'm going to start from 0 anyway. I don't care if that data stays. I only care about it while I'm running so that the different processes can see each other's numbers. But once I'm dead, whatever. So this means I don't have to wait for the data to get committed to disk. And now that's not slow anymore, because when I'm writing to disk, I'm only writing to a little bit of memory where the OS keeps a list of things that it's going to write to disk, which is absolutely cheating. But it doesn't mean you can't do it. I just happen to have an unusual situation where I can get away with pretending to use disk without actually paying the price for it. So, is memory fast? Are disks slow? As I've been saying, depends on the context. So, we've covered a lot of weirdly specific ground pretty much all over the place right now, right? But what is the point of me being here? What am I trying to say? There's this really old saying when talking about performance optimization. You've probably heard it. Measure before you optimize. Because the thing that you think is slow is probably not the thing that is actually slow. And most of us know this, and when I was trying to figure out where the code was spending time, I definitely measured and I definitely found surprises, right? Like the expert said, they were right. But what I found in this project is that that's not enough. As I said in the beginning, this is not a talk about memory or disk or microseconds, files, or hashes. This is a talk about assumptions. When we decided that the solution to a problem where we needed to do something really fast was to put stuff on disk, I was shocked. I was completely stunned. And the reason I was shocked is that, like everybody else, I knew that disk is really slow, right? And in fact, if you had told me before this project that Marshall dumping a whole hash into a file, it was going to be twice as fast as hitting a localhost Redis server, I would have laughed you out of the room, right? Because I just knew that wasn't true. But here's the problem with these things we all know. They're normally very simple. They're very memorable. And they have to be if they're going to spread and stay in our heads, right? Like, Ruby is slow, or Ruby can possibly be that slow. I mean, surely you can read and write the hash in under a microsecond. Now, can you? Yes. Can we? No, we're doing something weird with them for good reason, and it turns out to be slow. Memory is fast. Disk is slow. Redis is fast because it doesn't use disk. Now, is it fast? Yeah, for a database, it's really fast. Is it faster than disk? It depends. The problem is that there's a lot of nuance behind these simple truths, and they get lost in the process. If you look at them up close, these questions aren't simple. They don't have straightforward answers. And everyone that believes them hasn't actually checked them in the context of their own problem, because, of course, no, we already know they're true. But the reason that's a problem is that having these things we all know are true is going to make you blind to potential solutions that you could otherwise see if you didn't have this knowledge. Take this example, for example. It's not like we all got together and we discussed the options and we said, no, disk is probably going to be too slow. Didn't even cross our minds, because intuitively, we all just knew it wasn't going to work. Now, I happened to find this by pure luck. I happened to notice that the memory maps were opening a file anyway, and it would be very easy to make them do the same thing without the memory maps, and so I tried it. But I didn't try it because I thought it would be a potential solution. I just knew it wasn't going to work. I just wanted to know how ridiculously slower it would be. And if I hadn't, to this day, I wouldn't sleep well, wondering when that segfault was going to hit someone in production, right? So what I'm trying to say is, when you're trying to solve a problem and figuring out how to approach it, try to be aware of that filter at the back of your mind that's discarding options because you know they wouldn't work. Try to pause and look at those options. Why do you think they wouldn't work? Are you sure that's actually true? Can you do a little experiment? Can you measure it? Because there may just be a really simple solution that you're missing because it wouldn't work. Sometimes it does. Thank you.